Hello students, welcome back. In section 1 we did a lot of theory, concepts, techniques, and some applications of interval estimation. But believe it or not, they're all for introduction. The real deal did not even begin yet. The real applications will be covered in sections 2 and 3, and to a certain degree in section 4. Of course, that doesn't mean you can forget about all those things we did in section 1, because we're going to be using those in real application problems. Okay, here we go. Let's begin section 2, interval estimation for binomial proportions. What is binomial proportion? Well, here's a reminder. A binomial random variable is an independent repetition of Bernoulli random variable, which is defined like this. A random variable with only two possible outcomes, success, failure, and nothing else. The payoffs are 1, 0, and nothing else, and the probabilities are p, 1 minus p, and nothing else. That's Bernoulli random variable. And now, you can apply the expected value and standard deviation formula for Bernoulli random variable to get these two. It's not too difficult to get this, but this one is a bit hard. So you'll simply have to take these as formulae. But if you want, you can go through the proof like this. Most of the students wouldn't really care. Now, that's Bernoulli random variable, and binomial random variable is an independent repetition of those. So this is a single roll of die, or a single toss of coin, or a single draw of ball from an urn. But if you repeat that independently with replacement 5,000 times, now we have binomial random variable. Depending upon what viewpoint you take, you have two types of binomial random variable. Binomial random variable for the sum, or that for proportion. The latter one is important for us. Previously, we used to call it binomial average. Now, we're taking a different perspective, so same thing is being called now binomial proportion. It's a normal approximation, so it's based upon the central limit theorem. So we have the same mu. Expected value stays the same, so mu value stays the same. But standard deviation, that changes. We have sigma over square root of n, and that leads to this formula here. Here's a brief explanation. We have sigma over square root of n, and that's coming from the central limit theorem. And of course, the expected value stay the same. So expected value is just winning probability p. And sigma is square root of p1 minus p, and divide by square root of n. So simplified like this. Why did I tell you that derivation? That's because I see this answer or this mistake a lot, really a lot, I mean. That's wrong. N should be inside of that square root. Why? Because n comes from central limit theorem. It has its own square root. It's inside a square root. Algebraically, it goes inside a square root like this, but still, it comes with square root. It should not come outside of the square root. That's why I told you the derivation. Alright, please do not make that mistake. This formula is very, very important, and I usually call it formula number 2, maybe number 3. And okay, I'll say formula number 2, tied at 2. This one and this one at number 2, tied at number 2. Formula number 1 is z-score formula. Alright, so much for the binomial proportion formula here. And then let's talk about an application. Here's one. In a poll conducted by Harris Interactive of 1,179 video gaming US youngsters, 8.5% displayed behavioral signs that may indicate addiction. And then we have to answer these questions. Let's see, I don't remember exactly when, what year this took place, but it's coming from the real data. I actually got it from the textbook, and the textbook actually has a link, so it's got to be true. If I remember correctly, it came from USA Today newspaper. Anyway, all right. Let's begin. This problem gave us two numbers. Sample size of 1,179, pretty clear. And then observed proportion of 8.5%. And by the way, this is an observation, so it's not really accurate. So let me use approximation notation there. Now, from these two, you should immediately see that you can get the standard error. So go ahead and do that. Standard error is square root of p, 1 minus p over n. Therefore, it is equal to approximately square root of 0.085, 1 minus of that, and divided by 1,179. And if I calculate that using a calculator, which I'm doing right now, oh yeah, that's what you're supposed to get. Okay, you have all those numbers. Now let's go to the problem here. Find the 95% confidence interval associated with this poll result. So what did you do for 95% confidence interval in section 1? First, you have to draw the picture. Yes, you must. You absolutely must draw the picture. It's a required component of all my exams. So you have to draw the picture and label it accordingly. Let's see, I have only x bar here, but instead of that, that's a proportion, isn't it? Observed proportion is 0.085. That goes to the center here. And then 95% here, that means the other 5% should be shared by left and right. So 2.5% there, 2.5% there. The left-hand side endpoint is this center minus the margin of error. This one is this expected value plus the margin of error. So we are looking at something like this, 0.085 plus or minus. And then what is the margin of error? Margin of error, do you recall, is the z-score times the standard error. Recall that. We established it from section 1, which is 0.085. As a matter of fact, here, let me just use symbolic expression. Observed proportion, so let me use p here, and then p value is 0.085, yes. And now, never mind about this bar. There's no reason to make things more complicated than necessary. And the z-score for 95%, and the standard error we calculated, it's right here. And then as for the z-score for 95% confidence level, what is it? Do you recall? 2.5% here to the left, and standard z-table talks about only the left-hand side shading, so we have to look up 2.5%. And what do you get if you do that? You're going to get plus or minus 1.96. Minus 1.96 for here. So by symmetry, plus 1.96 for there. So it's plus or minus of that. And if you calculate it, you're going to get this and that value. I'll leave you here. Instead, I'll go back to my notebook here. Here's the visualization. Okay, 0.085, and then minus something, plus something, so that we have these two. About 7% and 10%, it appears. Here's the solution. Yeah, n value and observed proportion, the point estimate, and standard error computation. The formula number 1, n minus center over SC from that picture, n minus center over SC. If you do that, and for 95% confidence level or 2.5% to the side, you're going to get plus or minus 1.96. Plus or minus because of the symmetry. Remember, normal picture is symmetric. So from minus 1.96, we get this. From plus 1.96, we get that. And then you end up with this interval. About 7% to 10%, or 6.9% to 10.1%. Oh, by the way, if you use bracket notation, that's fine with me too. Here in this notebook, I decided to use parentheses. Most of the time I use brackets. I don't know what I was thinking. Okay, that was for 95% confidence interval. Oh, by the way, if I change the confidence level to something else, like for example, 97% confidence level, things will change a little, of course. So the other 3% will be shared by the left-hand side and right-hand side. So 1.5% there, 1.5% there, and you'll have to look up the z-score associated to that 1.5% shading. Well, I'll leave this z-table to you, but if you do it right, you're going to get 2.17. What if I change this into, let's see, 97%? Okay, let's go to say 99%. Same thing, 99% here, 0.5% there, 0.5% there. And then if you look up the z-table and then do estimation, 2.575 approximately speaking, you're going to get that. I'm going to leave the detail about z-table to you. Okay, so much for the confidence interval problem, including some change of numbers. Now let's go to the next part. Fill in the blank. No less than blank percent of the youngsters show the sign of game addiction with a 99% confidence level. What is this? No less than blank percent. What does that mean? So no less than means should be more than. The more than that percent point of youngsters is associated to 99%. So what is it? Is it lower confidence bound or is it upper confidence bound? It is lower confidence bound. No more than 1%. Excuse me. No more than blank percent. No more than blank percent here will capture 99%. Is it confusing because there are too many percentages? Sorry about that. That's the nature of proportion problem. So there are all kind of percentages going on here. The proportion itself is percentage, and then probability is also percentages, and both are decimals between 0 and 1. Sometimes confusing. Anyway, here we're looking for the lower confidence bound. So you have to look up the z-score associated to 1% here because the other is 99%. And if you do that, you're going to get about 2.33. So the center minus the margin of error, center minus z times sc, z-score will turn out to about 2.33 if you look up correctly. And then if you want to do it from scratch, here we go. N minus center over sc is about negative 2.33. So if you look up the z-table, probably you're going to get this. I got a little bit more accurate figure using Mathematical's estimation. So 326, I got like that. But actually 2.33 is what you can get from there. If you do a computation, you're going to get this. So what if I change this into, let's see, not 99%, but change, say, 95%, for example. You're going to get something like this. And then this is the lower confidence bound. That's 95%. Whole 5% is there. And you have to look up the z-table about whole 5%. Not 2.5%, but whole 5%. If you do it right, you're going to get about 1.645. All right, so much for confidence level and confidence bound problems. We're going to talk about sample size problem in a separate video.